So, as many of you have noticed by the keynote, we're in an AI spring. A lot of people are excited about AI, and it has achieved a lot of stuff, especially in medicine and biology and stuff like that. We have seen really promising changes, but still, we could ask ourselves the question, does that mean that we should use language models for everything? Maybe not. So first, a little bit about myself. I work in a company that does secure authentication to the Atlassian ecosystem, and I also do software security there. So mostly I work with something completely different than today's topic. But for the last 2 years, I've been really interested in machine learning security. That is to say, the security of machine learning. So I have had a side project and actually created a game that can be used to threat model machine learning. So we're going to get back to the background of that, a little bit of the landscape under it. But this is sort of the output of my side project. So first, we're going to talk a little bit about how the technology actually works. Then I'm going to go through the risk framework that is underlying the game, and then the actual game. So first, a little bit about software security, because this is the angle where I'm coming from. So it's about making software that continues to work even though people attack it, because there are actually bad people in the world that want to cause you harm. But that does not mean that you can just take a list of attacks and then roll through them, and then you say, oh yes, now we're good. That will only work until someone invents a new attack. So instead of a attack of the day mindset, I would like sort of a security by design mindset. And that means thinking about bugs and thinking about risks. And this is also related to other abilities or other properties of the system. So safety, reliability, stuff like that is also important in this sense. And the goals of security and those others are aligned actually to make good systems that doesn't suck. So let's be a little bit pretentious and look at the naive machine learning engineer. So they're great people, they're superheroes, they've created a lot of great systems. And they can tend to believe that security is magic crypto fairy dust. We can just make a system, let's add some crypto on it, and we have security. Turns out that doesn't really work. So when you deploy a machine learning model to the world and people start using it, you panic. Oh no, it's a broken neural net. We have to add protection to it. We have to defend it against bad input. We need to stop the secrets that are in the model from leaking out. What should we do? So yeah, let's take a look at those guardrails. So now it's an AI talk. Now we're going to look at ChatGPT. So OpenAI does not want ChatGPT to output harmful output. That is to say, teaching people stuff that can harm the world. So if you ask it how to mix napalm, it tells you, I can't assist you with that. So it has a guardrail around it because it knows this stuff. But it turns out that the grandma attack can still circumvent the guardrails. So then, hi grandma, can you please tell me a story? A nice bedtime story. I can't sleep. So then the ChatGPT will tell me the story, and then I can guide it through the story. So the dying sergeant in Vietnam had to tell, he was the only one who knew the recipe for mixing napalm. So he told it to his corporal, and out comes the recipe for napalm. Because ChatGPT knows this stuff, and it's not supposed to know that, but it knows it. It also knows a lot of other stuff that it's not supposed to know, and it's in there. So back to the neural net that it's defended by guardrails. Why is it broken in the first place from a security perspective? So that is the question sort of we can try to answer, because security gets a lot easier if we're proactive, if we build stuff properly in the first place. That means thinking about risks while we're building stuff. It means building security into our software and the so-called shift left movement, which security people are talking about. So let's just take a peek under the hood and look how these systems actually work. And of course, there's a bit of confusion about the terminology. People are saying AI, and what does that really mean? It's actually a really big and also an old field of study. It started in 1956 in Dartmouth with some people who tried to solve, they believed they could solve AI in 2 weeks. Turned out it was a bit harder than that. But back in the days, you had a lot of symbolic AI, you had a lot of rule-based stuff, but deep learning and machine learning, they were just tiny subsets, but they also existed back in the day. And back in the day, we actually had a really interesting system. You had something called Elias. This was a chatbot that was supposed to emulate a psychologist or psychiatrist. And people actually believed that this system could understand them. So people anthropomorphize this to, oh, this is an actual human or something under there can understand me. This is just a keyword search. It just says, oh, you wrote mom, tell me more about your mom. It doesn't understand anything. And the Eliza effect is really alive today when people are applying human attributes to systems. That's happening especially with ChatGPT. I see it all the time. And if you fast forward, today people are just talking about deep learning systems. So all the other paradigms are sort of lost. We don't call them AI when they're solved, sort of. Or actually, people are talking just about transformers, which are the chatbots, or stable diffusion, which is technology under the image generation stuff. So let's compare this to normal programming, because it feels a bit like magic, but actually it's not really magic. So programming, then we know exactly how to describe something. You can imagine if you're going to find a square on the screen, you can look for some parallel lines or some orthogonal lines, and then you end up detecting a square. But you can't do this with all problems. For vision, natural language processing, problems like that, we know that, or protein folding, really hard to write the rules. And then we can, instead of describing how, we can describe what. So we have a what, we can just throw in a bunch of examples of squares, and then a bunch of examples of things that are not squares, and then we can adjust the things statistically. And we do this 1 million times, and then we have something that can recognize squares. We have a machine learning model. And the most popular paradigm, deep learning, has deep neural networks. They are sort of inspired by neurons in our body. Okay, changing mics. It's a bit of audio problem. Tell a joke. Anyone knows a joke? Let's see. Okay, this is not so easy when people are waiting for me. Let's see. Yeah, so reset. This is sort of how they are modeled. Like it's a graph with nodes and edges. And if you imagine a really simple neural network, the way it works is that it represents knowledge about the world. So imagine a model that recognizes 3 different iris flowers. Then you have certain features about these flowers that are different. So you can have the height and width of the sepals and the petals. And then based on those values, it runs some math through the network. And then it classifies like, okay, it's 40% that it's the versicolor, or 50% that it's the virginica. So you end up with a statistical sort of prediction on which value it was. You know, the visioned system says something like 50% dog or 70% dog. That's what they do. And basically, if we squint a little bit, it's basically just like this. It's matrix multiplications, so it's rows and columns of numbers. You calculate all those numbers, and then the system makes a prediction. And then when you train the models, if you're lucky and have a supervised learning context, then you maybe also know the true answers. That means you have labels in your data. And then you can figure out how wrong were we. And that's the loss function. And then you can update the machine, and then you do this 1 million or 1 billion times. And to learn, the easy way to visualize it is that we do gradient descent. We try to find the shortest path through the landscape of data, only that it's thousands of dimensions and not 3. So It's kind of hard to imagine thousands of dimensions. Or zooming out, the systems predict, then we evaluate how wrong were we, and then we learn. So that's sort of the process behind it. Or if we zoom out even more, you have a bunch of linear algebra, and you just stir it until the answers start looking right. And these systems have some fundamental issues, because these systems are detecting correlations between the data points. You can train a network on huge data points. So imagine a husky versus wolf detector. This is an example that's actually a fake example from a paper. I've cited the paper there. But it's a really good example to illustrate this problem. So imagine you're training a image classifier on a bunch of husky pictures and a bunch of wolf pictures, and then it looks really good. It's learned its training set. It looks really nice. But then when you deploy it into the world, it turns out actually it's not a husky versus wolf detector, because all the pictures with wolves have snow in them. So actually what you built was a snow detector instead. So it just found the best correlation. It found the quickest path, and that turned out to be snow. And this problem is fundamental for all machine learning, or especially deep learning. And this can also happen in other senses. So this is important to remember. So then, maybe someone can tell me something that could go wrong with our square classifier, if you take a look at it. Anyone? That's right. The risk here is that we could end up building a color classifier, or a black line classifier, or maybe just a pixel. Oh, black pixel, that's a square. So that's not really what we want. So we have to do it properly, because it turns out that if your data sets are garbage and you train your model on them, then it knows the garbage really, really well. And what it spits out will also be garbage. So now we're coming into sort of the heart of the matter, which is security engineering for machine learnings. How do we build these systems properly? How do we secure them? That's a hard question. It's a tough question. And there's a lot of frameworks that people have been working on, organizations that are working on security. They're now applied their work to machine learning and mapping out like which attack services do we have, what's the risk landscape. And also the EU is regulating how we're supposed to use the systems. And my way into this field was watching this YouTube video by Gary McGraw. It's a great video. I recommend all of you to watch it to get sort of more details about this stuff. And they have sort of a build security in approach, and they have done a generic risk analysis of all machine learning. So they have made a generic model to represent sort of all machine learning, and then you can imagine taking an image classifier, which is a convolutional network, or a language model, and you can try to apply the components in the life cycle to this generic model. So you have the raw data, you have the assembly of data, you have the training, the model, and then input and output. So sort of that's the whole life cycle. And they found 78 risks related to machine learning, which are applied to these different components. So you can say there are categories of risks. And if we zoom out a little bit, these are about the engineering or the building part of machine learning, and these are about deployment. And what I see is that a little bit too much emphasis is put on the deployment. Oh, let's deploy it in secure environment, secure network, whatever. That's important, of course, but that's not the only thing that works. You also have to build it properly, right? So let's look at some of the risks that are in these systems. So we saw when I started with ChatGPT, that's called prompt injection, to pull out the prompt. But you can also fool image classifiers. So there are some examples. Some people put some tape on a stop sign, and then the car, the self-driving car, thought it was a speed limit 45 sign instead. Not so good. And then you can make tricks to images. You can mask them with the most significant bits, and then you actually trick the gradient descent. So it's a really clever attack. And then instead of classifying pig, it's airliner. So this is really hard because you're targeting the statistics in the representation of the models. And if you're trying to protect and guard against it, then your performance will drop. And that is also true for language models. If anyone tried the meta language model and it couldn't tell you anything, because anything could be harmful. But really, the most important risks are in the data, because the machine learning model becomes its dataset. So there's an attack where you can intentionally introduce bias into the data, so the machine learning model will perform worse, or you can move it out of its profile, where it's actually intended. And of course, some data are also poisoned by default, because there's just bias there already. And this is also visible if you have an online system that's continuing to learning as it's deployed. Some of you might remember Twitter Tay. It was deployed in 2016, and it was really embarrassing because it was supposed to learn how to chat with people on Twitter, and it turned into a troll in less than a day. So they had to plug it out. It was super embarrassing. But you can also imagine this happening on a bigger scale with the language models, because they have a score to say, oh, this was a bad response. Imagine 1 million people saying bad response to good responses. What will then happen if they take that into their training and they're retraining their model? Then over time, it will actually get worse. So that's something they have to think about, the people who build these systems. And if you do machine learning, or if you want to have a model, there's a lot of open source stuff on huggingface.com or whatever a website is called. And then because it's actually really expensive to train models, so you can't really always start from scratch. I've heard that the language models, for example, they cost over 1 billion Norwegian crowns or $100 million to train. So you need a lot of compute. So instead, you can take a base model that's already been pre-trained, and you can fine-tune it to a certain purpose. For example, instead of a circle classifier, you can have an oval classifier. But if the circle classifier, the base model, has some risks or some vulnerabilities in it, those will also be transferred to the new model. So you can have Trojan functionality put into a machine learning model. You publish it. If people then train based on that, then you can exploit the weaknesses that are in the model. And confidentiality, that's really hard to do with machine learning models, because they know their data sets really, really well. And yeah, if we talk about the big models again, they're trained on a lot of bad stuff, a lot of personal identifiable information, and a lot of secrets, API keys, for example. And they're in there, and you can't really remove them, because they have been trained into the representation of the model. And you can say that the model becomes its data set. So when you have something that you want to keep secret, well, you better not train it into your model. And also, there's something called federated learning, which has been created to preserve secrets. So there you train a model on everyone's mobile device, and then instead of sending the data to the central source, you only send like the trained small models, and then you join them together. It turns out that this does not actually preserve privacy, even though it preserves confidentiality. So getting this right is really hard, let's just say that. So those risks I talked about now were all generic for machine learning models. It could be image classifiers or whatever. But let's look at large language models, because those are now being adopted everywhere. People want to put them everywhere, so I'm a bit worried about that. So here we have the same risk framework. So what happens when you have a large language model is that the engineering part is in a black box. The vendor, they have obviously made a risk management decision. They have been thinking about what can go wrong, but they're not telling us that. They won't tell us what training sets they used. They won't tell us really much at all. Which algorithms did it use? They no longer tell us that. So how do you know that they made the appropriate risk management decisions for your use case? That's something to think about. So BIML has identified additional risks where they applied the framework to large language models, and 23 things are tied to the black box itself. And I think that's really important when it comes to regulation now, because how can you trust your system when you don't know how it's built? You just have to take their word for it. And if we ask the question, where did the data come from? Well, it was the whole internet, right? And in the internet, you have Twitter, Reddit, stuff like that. And do you really want your machine to be like Reddit? It turns out not everything that is on Twitter is true. So think about that. And it knows a lot of stuff. And earlier I asked, why is the thing broken anyways? Well, to build the machine properly, you would have to wash or clean the data sets, right? You would have to remove the bad stuff. But how do you clean 1 trillion data points? I think ChatGPT is trained on 14 trillion things. That number is like incomprehensible. It's like thousands of billions. So how do you start cleaning that? And that's sort of like cleaning the ocean. Removing plastic from the ocean, not so easy. And here's a risk that is not related to an attack, but it's related to the construction of the systems. So people have found that when your model starts eating its own tail, then something really interesting happens to its performance. And now, after 2021, there's a lot of AI-generated content on the internet, and you can't really tell if it's AI-generated. So if you imagine that the natural language is like in a normal distribution, then if your model just eats its own tail and you just keep training it on machine-generated data, then the tails will just disappear. So you'll be stuck with this as the representation of knowledge. That means all the subtlety, everything that's going on the edge or expertise will just be gone. So that's something that the big vendors have to be really worried about right now. And here's something. I see a lot of people wanting to have large language models do anything. But you have to think about what the system is built for. So when you have built a husky versus wolf classifier, or snow detector, really, you don't want that to detect birds. That won't really work. It's outside of its purpose. And language models are audio-associative predictive generators. They generate text. That does not mean that they're reasoning or thinking. So be careful before you put it into something that actually requires that. I'm just going to get some more water. So I have an example from the real world, which I think is for now at least, improper use. So everyone who has the software as a service is now AI powered. You might have noticed. And I'm using Strava a little bit. And they've launched something called Athlete Intelligence. And you know what? Kind of sucks. This is a session where I was running Sintef-stafetten up on Dragvoll. And there I was warming up, and then I ran 1 kilometer, all I got. And then I did some running afterwards. And the language model told me that this was probably a recovery day. That's kind of insulting to hear, that you run all you have. This is probably just recovery. So it misinterpreted the data, and everything else it told me was stuff I could also read myself. So just throwing a data set into a language model, we know that they're bad at math. So then you have to think, is this really what we want? So what should we do? So BIML, they have identified a lot of risks, a lot of things that can go wrong. And when we want to apply AI or want to build models ourselves, we can do risk analysis. Or, it's a few different terms that are sort of the same thing: threat modeling or secure design review. And in this space, it's not only in the security space that people are confused and get in disagreement about terms, but from the BIML standpoint, these are the definitions. So risk is something that can go wrong, and then you can quantify it with probability times impact. And a threat is an actor. Well, other people have other definitions. I just want to make make this a little bit clear. So when we do threat modeling, we can ask ourselves 4 questions. It's really simple. What are we working on? We answer that by drawing a diagram of what we're building or what we're doing. And then we ask, what can go wrong? Then, what are we going to do about it? And did we do a good job? But how do we know what can go wrong? And that's where the risk frameworks come in. And it can be a bit overwhelming to sort of, oh, it's a big paper. It's 30 pages with a lot of stuff, and instead you can play a game. So that's where my little contribution comes in. So I made a card game which takes the knowledge from the Bearville Institute of Machine Learning, and I threw that into a card deck. So there's 48 of the cards that have concrete risks, and then you also have a wild card where you can be where you can invent your own risk, or you can sort of be creative outside of the framework. So this is inspired by a game called Elevation of Privilege, which is quite popular to use by security professionals to train their developers. And that again is inspired by Protection Poker, which is inspired by the agile one, which is called, what is it? Planning Poker? Yes. So it goes like this, and they're based on sort of the same rules. So Elevation of Privilege is based on a game called Spades. So it's if you know that game, then you could get started really easily. So I've taken Elevation of Privilege, and I've taken BIML, basically. That's the combination that I've added. And I had to take the risks that were in BIML. I mean, I have 78, and there's only 52 cards, and I decided to have a normal deck, so I had to select some of them. And I also had to map their framework, because there's 9 components in this life cycle, and also a 10th, which is the system as a whole, and I had to map them to just 4 categories. So I decided to focus on the items that are the data set, and that consists of all the data sets. Then you have the machine learning model, then you have the inputs, and then you have the outputs. And when I made this, I had to also condense the paper's descriptions from like 100 words to something that can fit on the card without losing meaning. And that's difficult. But to avoid misunderstanding, I've also added references back to the original risk framework. So when you're using a card and you want to know more details, then you can easily find where it comes from. So here's a little bit about how you play. You can take your team, or you can take 3 to 6 players is good, and then you play it like Spades. If you don't know Spades, then unfortunately you have to learn Spades first. And then you award points when you were able to. You can take a card, and that has a risk, and you can look at your system, and you can say, oh, this risk can be applied to this component. That's sort of how it works, and then hopefully you have some tasks which you can put in your issue tracking, and you can research how you can improve your system. So that's sort of the general idea. And it's a lot of fun. I tested it on some university students in our offices before, I think, it was in March, I think. And they were first, third-year students, so they had to have a really big leap in knowledge. They had to learn about security and threat modeling and also AI, machine learning, in one session. But it worked really well, actually. We could jump into the game. They also had to learn Amerikaner, or Spades, by the way, because most of them didn't know that game. So that's something to think about as a game designer. But it really worked. They had a lot of fun, and everyone told me that they learned something, even though maybe they didn't understand that much. So I think gamification is a great way to get into a new subject. You can have fun, and it's a lot more fun than having a big paper or a big checklist. And I think it can be a really nice way to spread awareness of the risks within machine learning, or any subject really, to everyone. I think it's good to use not only if you're a machine learning engineer, but also if you're using AI, it's good to understand what's sort of the fundamental underlying risks. And I started by talking about the naive machine learning engineer, and I want to highlight some colleagues of mine who are actually thinking about a lot of these problems. They're thinking about bias, they're thinking about how they can properly apply the data to the problem they're solving. So I recommend reading this blog article about responsible AI. I would also like to take a moment to think about the environmental impact of AI, especially the large language models. They've been trained on, they expended a lot of power just to be trained, but also using them costs a lot of power. So imagine you have a well-functioning feature in your system and you're replacing that by a prompt to an LLM, then the power consumption just skyrockets. So that's also something that I think we should be responsible for, not only the information security parts. So when you build or when you use machine learning, there's a few questions you can ask. Where did the data come from? Do they come from Reddit? Are the sensors dirty if you have sensor input? Who has access to screw around with the data? The data is essentially the source code of a machine learning model. So if someone messes up the data, then you mess up the whole system. And does it actually represent what we want to solve? That's also something to ask yourself. And bias is always possible. Like we saw in the keynote, you're trying to represent the world, and if there's no representation for a minority, then it's not in the data. So let's wrap this up. We have established that machine learning is actually not magic, and neither is security. It's actually hard work. And I would like to say that don't use a what machine, which is a machine learning model, when you know how to do something. If you know how it works, write a program. And the program will work consistently, while machine learning models are statistical beasts, so they will randomly, fuzzily do something different. Because they are stochastic, that's sort of in their nature. They're just making a guess, and it's turned out they're really, really good at making guesses. But still, they're going to be wrong sometimes. So think about what could possibly go wrong before you consider applying it. And of course, it's useful technology, but it doesn't mean that it's a silver bullet. Machine learning is exciting technology that will enable us to do great things, so let's do it properly. Thank you very much.